By the end of this video, you'll learn how we can represent the words, numbers, emojis, and more we see on our screens from only these 256 possible values. It's all thanks to character encoding. Character encoding is used to assign our binary values to characters so that we as humans can read them. We definitely wouldn't want to see all the text in our emails and web pages rendered in complex sequences of zeros and ones. This is where character encodings come in handy. You can think of character encoding as a dictionary. It's a way for your computers to look up which human character should be represented by a given binary value. The oldest character encoding standard used is ASCII. It represents the English alphabet, digits, and punctuation marks. The first character in the ASCII to binary table, a lowercase a, maps to 011000001 in binary. This is done for all the characters you can find in the English alphabet, as well as numbers and some special symbols. The great thing with ASCII was that we only needed to use 127 values out of our possible 256. It lasted for a very long time, but eventually it wasn't enough. Other character encoding standards were created to represent different languages, different amounts of characters, and more. Eventually they would require more than 256 values we were allowed to have. Then came UTF-8, the most prevalent encoding standard used today. Along with having the same ASCII table, it also lets us use a variable number of bytes. What do I mean by that? Think of any emoji. It's not possible to make emojis with a single byte since we can only store one character in a byte. Instead, UTF-8 allows us to store a character in more than one byte, which means endless emoji fun. UTF-8 is built off the Unicode standard. We won't go into much detail, but the Unicode standard helps us represent character encoding in a consistent manner. Now that we've been able to represent letters, numbers, punctuation marks, and even emojis, how do we represent color? Well, there are all kinds of color models. For now, let's stick to a basic one that's used in a lot of computers, RGB, or red, green, and blue model. Just like the actual colors, if you mix a combination of any of these, you'll be able to get the full range of colors. In computer land, we use 3 characters for the RGB model. Each character represents a shade of the color, and that then changes the color of the pixel you see on your screen. With just 8 combinations of zeros and ones, we're able to represent everything that you see on your computer, from a simple letter A to the very video that you're watching right now. Very cool. You might be wondering how our computers get these ones and zeros. It's a great question. Imagine we have a light bulb and a switch that turns the state of the light on or off. If we turn the light on, we can denote that state as 1. If the light bulb is off, we can represent the state as 0. Now imagine 8 light bulbs and switches. That represents 8 bits with a state of 0 or 1. Let's backtrack to the punch cards that were used in Jacquard's loom. Remember that the loom used cards with holes in them. When the loom would reach a hole, it would hook the thread underneath, meaning that the loom was on. If there wasn't a hole, it would not hook the thread, so it was off. This is a foundational binary concept. By utilizing the 2 states of on or off, Jacquard was able to weave intricate patterns into fabric with his looms. Then the industry started refining the punch cards a little more. If there was a hole, the computer would read 1. If there wasn't a hole, it would read 0. Then, by just translating the combination of zeros and ones, our computer could calculate any possible amount of numbers. Binary in today's computer isn't done by reading holes. It uses electricity via transistors, allowing electrical signals to pass through. If there's an electric voltage, we would denote it as 1. If there isn't, we would denote it by 0. But just having transistors isn't enough for our computer to be able to do complex tasks. Imagine if you had 2 light switches on opposite ends of a room, each controlling a light in the room. What if, when you went to turn on the light with one switch, the other switch wouldn't turn off? That would be a very poorly designed room. Both switches should either turn the light on or off, depending on the state of the light. Fortunately, we have something known as logic gates. Logic gates allow our transistors to do more complex tasks like decide where to send electrical signals depending on logical conditions. There are lots of different types of logic gates, but we won't discuss them in detail here. If you're curious about the role that transistors and logic gates play in modern circuitry, you can read more about it in the supplementary reading. Now we know how our computer gets its ones and zeros to calculate into meaningful instructions. Later in this course, we'll be able to talk about how we're able to turn human readable instructions into zeros and ones that our computer understands through compilers. That's one of the very basic building blocks of programming that's led to the creation of our favorite social media sites, video games, and just about everything else. Binary is the fundamental communication block of computers, but it's used to represent more than just text and images. It's used in many aspects of computing like computer networking, which you'll learn about in a later course. It's important that you understand how computers count in binary. We've shown you simple lookup tables that you can use like the ASCII to binary table, but as an IT support specialist, whether you're working on networking or security, you'll need to know how binary works. So let's get started. You'll probably need a trusty pen and paper, a calculator, and some good old-fashioned brain power to help you in this video. The binary system is how our computers count, using ones and zeros. But humans don't count like that. When you were a child, you may have counted using 10 fingers on your hand. That innate counting system is called the decimal form, or base 10 system. In the decimal system, there are 10 possible numbers you can use, ranging from 0 to 9. When we count binary, which only uses 0 and 1, we convert it to a system that we can understand, decimal. 330, 250, 240, 4 million. They're all decimal numbers. We use the decimal system to help us figure out what bits our computer can use. We can represent any number in existence just by using bits. That's right, we can represent this number just using ones and zeros. So how does that work? Let's consider these numbers: 128, 64, 32, 16, 8, 4, 2, and 1. What patterns do you see? Hopefully you'll see that each number is a double of the previous number going right to left. What happens if you add them all up? You get 255. That's kind of weird. I thought we could have 256 values for a byte. Well, we do. The 0 is counted as a value, so the maximum decimal number you can have is 255. What do you think the number is represented here? See where the ones and the zeros are represented? Remember, if our computer sees a 1, then the value is on. If it sees a 0, then the value is off. If you add these numbers up, you'll get a decimal value. If you guessed 10, then you're right. Good job. If you didn't get it, that's okay too. Take another look. The 2 and 8 are on, and if we add them up, we get 10. Let's look at our ASCII to binary table again. The letter H in binary is 011010000. Now let's look at an ASCII to decimal table. The letter H in decimal is 104. Now let's try our conversion chart again. 64 plus 32 plus 8 equals 104. Look at that. The math checks out. Now we're cooking. Wow, we've gone over all the essentials of the basic building blocks of computing and machine language. When we interact with our computers, we use our mouse, keyboard, or even a touchscreen. We don't tell it the actual zeros and ones it needs to understand something. But wait, we actually do. We just don't ever have to worry about it. We use the concept of abstraction to take a relatively complex system and simplify it for our use. Use abstraction to operate the transmission or the engine directly. There's a steering wheel, some pedals, maybe a gear stick. Abstraction hides complexity by providing a common interface. The steering wheel, pedals, gear stick, and gauges in our car example. The same thing happens in our computer. We don't need to know how it works underneath the hood. We have a mouse and a keyboard we can use to interact with it. Thanks to abstraction, the average computer user doesn't have to worry about the technical details. We'll use this under the hood metaphor throughout the program to describe the area that contains the underlying implementation of a technology. In computing, we use abstraction to make a very complex problem, like how to make computers work, easier to think about. We do that by breaking it apart into simpler ideas that describe single concepts or individual jobs that need to be done, and then stack them in layers. This concept of abstraction will be used throughout this entire course. It's a fundamental concept in the computing world. Another simple example of abstraction in an IT role that you might see a lot is an error message. We don't have to dig through someone else's code and find a bug. This has been abstracted out for us already in the form of an error message. A simple error message like file not found actually tells us a lot of information and saves us time to figure out a solution. Can you imagine if instead of abstracting an error message, our computer did nothing and we had no clue where to start looking for answers? Abstraction helps us in many ways that we don't even realize. In the last video, I mentioned that people don't need to understand how a computer works for them to use it because abstraction makes things simpler for us. That's technically true, but since you're stepping into the world of IT, you do need to understand all the layers of a computer and how they work. It's essential that you understand how the different pieces interact so you can resolve any issue that may arise. A computer can be cut into 4 main layers: hardware, operating system, software, and users. The hardware layer is made up of the physical components of a computer. These are objects you can physically hold in your hand: laptops, phones, monitors, keyboards. You get the idea. In the next lesson, you'll learn all of the components of a computer and how they work. You'll even be able to build your own computer by the end of this module. The operating system allows hardware to communicate with the system. Hardware is created by many different manufacturers. The operating system allows them to be used with our system regardless of where it came from. In the next few lessons, you'll learn about the major operating systems that we use today, and you'll be able to understand all of the underlying components that make up an operating system. By the end of these lessons, you'll have a strong grasp on the major components of any operating system like Android or Windows, and use that knowledge to navigate any operating system. The software layer is how we as humans interact with our computers. When you use a computer, you're given a vast amount of software that you interact with, whether it's a mobile app, a web browser, a word processor, or the operating system itself. Later in this course, we'll learn how software is installed on our systems and how we interact with different types of software. The last layer may not seem like it's part of the system, but it's an essential layer of the computer architecture: the user. The user interacts with the computer. The user layer is one of the most important layers we'll learn about. When you step into the field of IT, you may have your hands full with the technical aspects, but the most important part of IT is the human element. While we work with computers every day, it is the user interaction that makes up most of our job, from responding to user emails to fixing their computers. By the end of the course, you'll also learn how to apply your knowledge of how a computer works to fix real-world issues that can sometimes seem random and obscure. We'll do this by learning how to utilize problem-solving tactics to identify issues and solutions. There's a lot ahead. The next instructor you're going to meet is a friend of mine, Devin Sreetharan. And I know there's no better person to teach you about hardware. He'll even show you how to build a computer from its component parts. Pretty cool. We have a lot of people that have non-traditional backgrounds that have made it here at Google. I've worked with people who have history degrees. I've worked with people who have economic degrees. I think the benefit of run into problems of IT.